So let's go over homework 7 problems. I've already copy and pasted the data table for homework 7 in problem number 1 involving the hydrolysis of penicillin. And I went ahead and did the plots of V in the y-axis and substrate concentration on the x-axis. That's your Michaelis plot. And if it has this hyperbolic point that reaches an asymptote, then you know it follows Michaelis-Menten kinetics. And I also went ahead and plotted a double reciprocal plot, which is 1 over penicillin, which is 1 over substrate. And that would be on the x-axis, and on the y-axis would be 1 over the reaction velocity. In this case, the reaction velocity is measured by the amount that is hydrolyzed. So if you remember how to do these plots and working with Excel, then this should be easy. If for some reason you forgot how to generate these graphs and these plots, then go ahead and review homework 4, because in homework 4 I just gave a quick primer on manipulating and generating graphs with Excel. So instead of going over that one more time and being repetitive, I just went ahead and processed the data. So this is what you should have for homework 7, problem 1. The statement that it's asking for is Vmax and the turnover number. It's also asking if this follows Michaelis-Menten kinetics. The answer is yes by looking at the shape of this curve. And once you plot the double reciprocal plot, we are ready to get Vmax and Km. The question is asking only for Vmax. This is where you're going to have to know how do you calculate Vmax from the double reciprocal plot. Vmax is this asymptote region. It's really hard to
As you determine the y-intercept where this crosses the x-axis, the x value is going to be 0. So plugging in x equals 0 here, you get y equal to 1.462. So 1.462 nanomoles per minute, make sure you are aware of the units, is your Vmax. Now we have to determine the turnover number. So the turnover number is nothing more than Vmax over the total enzyme concentration, usually expressed in molarity. And remember, there's 4 important numerical parameters to determine how well an enzyme performs its function of turning substrate over to product. One is Vmax, the other one is Km, and then this one is called the turnover number, how much substrate gets turned over to product. And then the fourth one is catalytic efficiency, also known as Kcat over Km. So once we have our Vmax, we need to just determine total enzyme concentration and plug it into this formula. We're not given the concentration so directly. We know that penicillin has a weight of 29,600 Daltons. That's what is given in our problem. Penicillin has an atomic weight of 29,600 Daltons. That has nowhere near the units we want for concentration. However, we do know that 1 Dalton is 1 gram per mole. So 29,600 Daltons is nothing more than 29,600 grams per mole. So if I move back to my Excel, 29,600 grams per mole. We know that we have 1 nanogram that we worked with. That is how much of the penicillinase that we actually were converting to, that's how much enzyme that we were working with. That's how much enzyme that was working on penicillin to break down that lactam ring. And so we have 1 nanogram of it, which is nothing more than 1 times 10 to the minus 9 nanograms, grams. So if you want to put exponents in Excel, you just do 1 e to the minus 0.9, and you notice that you have 1 times 10 to the minus 9 grams. So 1 times 10 to the minus 9 grams divided by 29,600, the grams cancel, and that gives you the units of moles. And, well, concentration is usually expressed in moles per liter, or micromoles per liter, or millimoles per liter. Molar, really what it is. So what is the volume of the assay that we're conducting the experiments in? We're conducting this in 10 milliliters, which is nothing more than 0.01 liters. So going back here, we have 0.01 liters. And get the concentration in moles per liter, all we have to do is take the moles and divide it by the liters. And we get 3.38 times 10 to the minus 12 molar. Now, 3.38 times 10 to the minus 12 molar, that's enough to go and plug it into our equation here. And when you do that, if you take our Vmax, which is 1.602, divide this by 3.38 times 10 to the minus 12 molar, you get 4.32 times 10 to the 11. But look at your units, okay? Always be aware of the units. Vmax, which is a velocity, is in units of nanomoles per minute, and molarity is in units of moles per liter. So when you do the unit conversion, nanomoles per minute divided by moles per liter is nothing more than nanomoles liter divided by moles per minute. And that's not the correct units because you have nanomoles on the numerator and moles on the denominator. You could actually cancel them out. The way you cancel this out is by recognizing that 1 nanomole is actually 1 times 10 to the minus 9 moles. So if I take this and multiply that by 1 times 10 to the minus 9 moles, the moles cancel out, and I'm left with liters per minute. So this enzyme, penicillinase or beta-lactamase, turns over 432 molecules of penicillin per minute.
Now let's look at problem number 2 of homework 7. We're given our data table. This specific problem, you actually have the substrate concentration listed, but you also have the addition of the inhibitor. So what does the inhibitor do when in the presence of the enzyme, and how will it affect Km and Vmax? And furthermore, what type of inhibition is it? Is it going to be a competitive inhibitor, uncompetitive inhibitor, or some specialized form of non-competitive inhibition? I've already put the data table in and have already computed the Lineweaver-Burke plot. So again, go to homework 4 for an introduction on how to graph this using Microsoft Excel. So let's first take a look at the Lineweaver-Burke plot, the double reciprocal. Here in the blue is without the inhibitor. Notice what the inhibitor does when you do this assay. It causes a counterclockwise shift. That is a stereotypical pattern that would result when you have any inhibitor, no matter whether it's a competitive inhibitor, mixed inhibitor, or uncompetitive inhibitor. You're going to have this counterclockwise or shift upward. Now we want to figure out Vmax and Km without the inhibitor, which is this blue line, and then with the inhibitor, which is this brownish line. So Vmax without the inhibitor, let's do that one first. Again, this is the y-intercept, and then we flip it to get Vmax. So the y-intercept is where x is equal to 0. We plug 0 here for the x value, and we get a y value of 0.0224, but that's not Vmax, that's 1 over Vmax. So to get Vmax, we have to flip it. So equals 1 divided by 0.0224, and we will get a value of 44.6. Now always put units. The units here are micromolar per minute. It's very important that you put units. A number is meaningless unless you put units by its side. Let's do the exact same thing with the presence of the inhibitor. This time we're looking at this brown line, and the y-intercept is where it hits the y-axis. The x value is 0, so plug in 0 here. You get 0.0222. That is not Vmax, that is 1 over Vmax. So to get Vmax, we flip it, 1 divided by 0.0222, and we get 45.045. So again, units are going to be very important. And we know of a situation where the Vmax is unfettered by the presence of an inhibitor, and that is competitive inhibition. So our first inkling is that this would be a competitive inhibitor. Let's calculate Km now. Minus I to the minus x axis, because this is Excel. Excel can't do that for us.
And where it hits the x-intercept is where y is 0. So we have to do a little manipulation here. Y is equal to 0. X is going to equal to minus 0.0224 divided by 0.224. So equals minus, I'll put a parentheses. Actually, I'll just do it as is. It's minus 0.0224 divided by 0.224. We have to take the negative reciprocal of that. So taking the negative reciprocal of, get a value of 10. Let's make sure we have our right units. The units of our micromolar and our Km is 10 micromolar. Remember Km, its units are going to be in concentration. So micromolar, millimolar, even molar, it's a concentration. And you should also know it's the substrate concentration where V is equal to V max over 2. In our mind's eye, we will extrapolate the brown line all the way to the minus x-axis. The y value is 0, so we solve for x. X will be minus 0.0222 divided by 0.6663. This is our value of the x-intercept. We take the negative reciprocal of that to get us the Km value in the presence of the inhibitor or apparent Km, and our value is 30 micromolar. Now notice here that our Vmax stays the same, but our apparent Km has increased. It has increased almost by a factor of 3. This is classic competitive inhibition. The fact that you can just simply outcompete the competitive inhibitor by adding more of the amount of the cognate substrate. This is just brute force outcompeting the inhibitor by adding more substrate. In this case, you can achieve the same Vmax by adding 3 times more the amount of substrate. I want to bring your attention to alpha. Alpha is a modulation factor. The alpha determines the degree in which this curve shifts counterclockwise. And alpha actually is this formula. The formula for alpha, or to what degree this gets this counterclockwise shift, is mathematically defined as 1 plus the inhibitor concentration over the inhibition constant, Ki. So Ki is an equilibrium constant, and that tells you how well the affinity is of the enzyme to the inhibitor. If the inhibitor and enzyme have a close affinity towards one another, then you would expect this to have a very high shift counterclockwise. It's going to shift more counterclockwise, essentially. If the inhibitor has a very low affinity for the enzyme, then you would expect the degree to which this shifts counterclockwise to be reduced. Now, this is a competitive inhibitor. We've already solved that because the Vmax is the same. You just achieve Vmax by bumping the Km from 10 to 30 micromolar. So really, the inhibitor is competing for the enzyme's active site. So once we have this modulation factor alpha, we have everything that we need to solve the equation for the amount of enzyme that's in the enzyme substrate form, as well as the amount of enzyme that is in the form of EI, enzyme inhibitor complex. So let's just quickly do that using Excel. So our Km without any inhibitor, we calculated that to be 46.64. So I'll just use Excel here. So equals 44.64 times the inhibitor concentration. The inhibitor concentration is 2 millimolar or 2,000 micromolar. And we will divide this by the apparent Km, which is 30.0135, minus our actual Km without inhibitor, and that's 10. We close those parentheses, and we get a value of 4,461. So that's the equilibrium constant in which the inhibitor and the enzyme will bind. So that number, how high it is, will tell you how closely the affinity is between the inhibitor and the enzyme. So now we are interested in the bound enzyme substrate complex relative to total enzyme, and that is going to equal your substrate concentration. Your substrate concentration is going to be 10 micromolar.
Your alpha, we have determined that alpha to be, well, we haven't determined alpha yet, so we have to get alpha here. So alpha is going to be 1 plus inhibitor concentration, which is 2000 micromolar, divided by Ki, which we already determined, Ki being this value. So the alpha value, or the modulating factor, which determines again to what degree this is going to be shifted counterclockwise, is going to be 1 plus the ratio of the inhibitor concentration divided by the affinity constant. So I can just plug that into my Excel. 1 plus our inhibitor concentration is 2000 divided by our Ki is 4461. Okay, all my equations are shown right here, and my alpha value, or my modulator, is 1.44 or 1.45. So this gets shifted 1.45. There's no real units to that. It's just a factor. So this gets shifted by a factor of 1.45. Let's plug that in here. Our substrate concentration is going to be 10 micromolar, and so we'll plug it in. So our substrate concentration is 10 divided by our alpha value is this times Km. Our Km is this value here, and we want to add that plus our substrate concentration is equal to 10. I want to just add an extra layer of parentheses, get my math correct, and this is our bound enzyme in the form of enzyme substrate. So about 41% or so of the enzyme is in the form of the enzyme substrate complex. Now we can also do the bound EI over ET, and let's take a look at that equation here. Doing that, our substrate concentration is still at 10 micromolar. So we have our substrate concentration at 10 micromolar, and that divided by our modulating factor alpha times the apparent Km, which is 30, and then all of that plus, I'll close the parentheses, plus our substrate concentration, which is 10. Just as before, I'm going to add an extra layer of parentheses to just get my math order correct. And we have about 18% of the enzyme is in the form of the enzyme inhibitor complex. Part D asks us to do this. Instead of a substrate concentration of 10, which is part C, we'll do this at a substrate concentration of 30 micromolar. We're going to use 30 micromolar, which is the concentration of substrate stipulated in part D. So everything else is the same. So we'll plug into that equation one more time for the bound enzyme substrate form. And now at 30 micromolar, we have 67% of the enzyme in the form of enzyme substrate complex. So you bump up the substrate concentration, you've increased the amount of the ES form from 41% to 67%. How much of this is in the enzyme inhibitor complex? We'll do the exact same thing here. This time we are at 30 micromolar. Our alpha modulator is 1.448. That times our apparent Km, plus we're at 30 micromolar. Again, let's keep our parentheses intact, and we have about 40% of the enzyme in the form of enzyme inhibitor complex. Finally, we can ask to determine the ratio. So let's take a look at our ratio between the bound enzyme substrate over the bound enzyme inhibitor. So to do that, we'll take the ratio of these two numbers here, 0.408 and 0.187. So if I take the ratio of them, this divided by this, I get 2.18. So most of the enzyme is in the form of the enzyme substrate. So for every 2.18 molecules of enzyme substrate, we have 1 molecule of enzyme inhibitor, because if you take a ratio of ES over ET over EI over ET, the ET total enzyme concentration cancels. What about the ratio here at 30 micromolar substrate concentration? Ratio here is 1.65. So that means that for 1.65 molecules of enzyme substrate, there is 1 molecule that is in the form of enzyme inhibitor. Let's look at problem number 3 here. And if you look at problem number 3 relative to problem number 2, everything is the same in terms of the raw data. The only difference is that the values of
the velocity in the presence of the inhibitor is going to be different. Here, instead of 4.1 and 6.4, 11.3, we got new values of 2.1, 2.9, 4.5. So the velocity, the turnover has actually decreased in the presence of this particular type of inhibitor. So we can go through all of this again. Let me show you a neat trick you can do in Excel. So here's the data that we already worked on, and we already answered all of this. So I'm just going to go to my tab, right-click, and I'm going to make a copy of it. So I'm going to make a copy of this. I'm going to create a copy. And here is my second version of the copy, so I'll just call it copy. And in this copy version, everything is the same from this tab to this tab that I just created a copy of. All I need to do is just modify these values here, and everything gets adjusted. So let's go here, and everything is the same between data table in problem 3 and data table in problem 2, other than the velocities. So if I can just copy and paste this array, copy, and let's go back here and plug it in. Right here, everything should correct itself, and everything has corrected itself. So now here's my new equation of the line. Here's my new equation of the line. All right, so let's do Vmax over NKM with the inhibitor and without the inhibitor. So let's first start out without the inhibitor. X is going to equal 0. We'll plot in X equals 0 here, and we will get 1 divided by 0.0224 as our new value. In fact, everything has stayed the same. So without the inhibitor, it's going to be, okay, what we're interested in is our new values over here as a result of this new inhibitor. So where this hits the y-axis is where x is equal to 0. So x is going to equal 0, y is 0.1125. That's not our Vmax. That is 1 over apparent Vmax. So let's take the reciprocal of that to get our new apparent Vmax. And we have 8.88. So our Vmax has gone down. Okay, what about our Km here? Km is where we extrapolate this to the negative x-axis. Y is 0. So our Km, or apparent Km, is minus 0.1125 divided by 1.1084. Minus 0.1125 divided by 1.1084. Close those parentheses. All right, take the double reciprocal of that, or the negative reciprocal of that, I apologize. Negative 1 divided by this number here, and we get 9.85. So here's our new values. Our Vmax has gone down, but our K sub m has actually stayed the same. So what type of inhibition is that? When your K sub m stays the same and your Vmax goes down, that actually means that these guys share a common x-intercept. Just as in our previous problem, if I jump back, in a competitive inhibition, these guys share the common y-intercept. Now these guys have the common x-intercept. So what type of inhibition is that? Well, it's a special type of mixed inhibition, and it's a non-competitive inhibitor. So part C of this problem, in problem number 3, asks us for the dissociation constant or the equilibrium constant. The apparent Vmax is right here. The concentration of the inhibitor that was given to us in problem C, problem 3, part C, is 100 micromolar, which is the same as 0.1 millimolar. But since everything here is in micromolar, I can go ahead and just leave it as micromolar. So we have our apparent Vmax times 100 micromolar divided by our Vmax here, and we get a value of 19.91. So that is our equilibrium constant. You can call it the dissociation constant for this non-competitive inhibitor. It's going to be the same. It's going to be the same because remember, non-competitive inhibition is a special type of mixed inhibition where the dissociation constant or the equilibrium constant is going to be the same whether the inhibitor binds to the enzyme or whether the inhibitor binds to the enzyme substrate complex.